All right, so colligative properties, just to be clear, this is a pretty standard first year university topic. This is not something you would study in high school chemistry. Um, but in the new AP exam, this is no longer covered. Okay, so this is not a topic that you're going to see on next year's AP chemistry exam. But if you take first year chemistry at university, this is a pretty standard topic here. I'm pretty sure at University of Manitoba. So I'm going to cover it. It's also interesting and it has some good mathematical applications. So when you dissolve solutes in a solvent to make a solution, I think it's pretty obvious if you think about it that a lot of physical properties are going to change. For example, water has a density of 1 gram per mil. But if you dissolve stuff in the water to make a solution, the solution's density is almost certainly not going to be 1 gram per mil, unless, of course, you were dissolving another substance that had the same density. But the density of the solution is not going to be the same as the density of the solvent almost always. Similarly, the vapor pressure above the solution is almost certainly going to be different than the vapor pressure above the pure solvent. Boiling point and freezing point of the solution are not going to be the same as the boiling point and freezing point of the pure solvent. So salt water does not boil at 100 degrees. Salt water does not freeze at 0 degrees. Their boiling points and freezing points are not the same as pure water. And then there's something called osmotic pressure. If you've taken AP biology or in the advanced biology class, you've probably talked about it there. We'll talk about that as well near the end of the section on colligative properties. A colligative property is a little bit hard to define. Okay, so people can list colligative properties, but if you ask them exactly what makes it a colligative property, most people can't give you a good explanation. So there are properties that change when a solute is added to a liquid, but there's more to it than that. So the properties change when you dissolve the solute. But the magnitude, the amount of change that you see, this is the most important part of the description. It depends not on the identity of the solute. So it doesn't matter what solute you add, but what does matter is how many solute particles end up in the solution. All right. So for example, sodium chloride has a sodium ion and a chloride ion. Potassium nitrate has a potassium ion and a nitrate ion. If you put 1 mole of sodium chloride into a liter of water, and you put 1 mole of potassium nitrate into a liter of water, in both of those situations, you'll end up with 2 moles of particles floating around in the water. You'll get 1 mole of sodium and 1 mole of chloride, 2 moles of particles floating in that solution. You'll get 1 mole of potassium and 1 mole of nitrate. You'll get 2 moles of particles in that solution. The fact that it's sodiums and chlorides versus potassiums and nitrates doesn't matter. The boiling points, the freezing points, the vapor pressures, the osmotic pressures should be the same, ideally, in those two solutions. That's why they're colligative properties: vapor pressure, boiling point, freezing point, osmotic pressure. Notice I left out of that density. Density will be different if you put 1 mole of sodium chloride versus 1 mole of potassium nitrate, the densities will clearly not be the same as water, but the densities won't be the same as each other because the molar masses are different. If you put a mole of sodium chloride versus a mole of potassium nitrate, you're putting different masses because they have different molar masses, and that means the densities will not be the same. So density is a property that changes when you add a solute, But density is not a colligative property because it does depend on the solute you're adding, okay? Changes to vapor pressure, changes to boiling and freezing points, changes to osmotic pressure, those are colligative properties. Anybody need more time on that? Okay. I think sketching this phase diagram is really important, okay? So I'm going to give you a little bit of time to sketch this. But before you start sketching, just look at it with me and I'll give you time to sketch. Just look at it to make sure you understand what you're sketching. So this is a phase diagram. We saw them in the liquids and solids unit. Pressure or vapor pressure on the y-axis and temperature on the x-axis. The black curve is, it says solvent, but from the shape of the curve, that's almost certainly water, isn't it? Because of this negatively sloped boundary to solid and liquid. So the black curve here is water, pure liquid water. You go up to 1 atmosphere on the pressure axis. If you went over and hit that black curve right here, you're on the solid liquid boundary. What are you finding if you go straight down to the temperature axis? Somebody. If you go to 1 atmosphere on the pressure axis and you go to the solid liquid boundary and you go straight down to the temperature axis, what are you finding?
The normal boiling point.
Almost the normal what?
Boiling point.
At the solid
melting
boundary.
point.
You'd be the normal melting or the normal freezing point, right? That's what you're finding there. Now, if you continue to go across and you hit the liquid gas, the liquid vapor boundary, again, we're looking at the black curve, and you drop straight down, what are you finding there? Someone other than Sir Reginald this time?
Would that be the boiling point?
That would be the normal boiling point, right? Because you're at 1 atmosphere pressure. So that's the normal boiling point. This is the normal freezing point or normal melting point. Now, what happens if you dissolve something in the water? Okay, now there are 2 kinds of solutes that we can talk about here. There are volatile solutes. Volatile means they evaporate, like alcohol, for example. And then there's non-volatile solutes, things that don't evaporate, sugar and salt, things like that. Make sure you know what those terms mean. Volatile solutes are things that evaporate. Non-volatile solutes are things that don't evaporate. We're only going to talk here about non-volatile solutes, solutes like salts and sugars, things that don't evaporate. I'm going to explain this in a few minutes, but take a look at this point on the graph, the original graph for water. When you add a non-volatile solute, let me get my mouse there. When you add a non-volatile solute, the vapor pressure drops to this point here. And you can pick any point on the curve. When you add a non-volatile solute, the vapor pressure drops. So every point on the black curve drops because you're dissolving a non-volatile solute in it. Now we'll talk about why it drops later. So after you've dissolved a non-volatile solute in your water or in your solvent, the new phase diagram is this blue one. So in your sketch, go ahead and sketch it if you haven't already been sketching. You want to draw the black curve first and label that the phase diagram of water. And then if you don't have another color, you can put a dotted line where there's a blue line on here and label that the phase diagram of the solution. Where you've dissolved a non-volatile solute, you now have a solution. And you want to make sure you understand that every point on the black curve has dropped. The vapor pressure has fallen as a result of adding a non-volatile solute. Why is that important? Why is it important that the vapor pressure dropped? Well, you now get this blue curve. Go back up to 1 atmosphere and go across, and what do you notice? The normal freezing point is no longer the same as the pure liquid's normal freezing point. Is it going to be higher or lower? The freezing point.
Lower.
It's going to be lower, isn't it? You hit the blue curve before you hit the black curve. So there's a lowering of freezing point. Freezing point depression is what we're going to call it. It's been depressed, it's been lowered. But what happens to your boiling point? This used to be the boiling point. Now the boiling point's over here. So what happened to the boiling point? It went
Higher.
higher, it went up. That's right. The fancy word for that, what we'll say is there's boiling point elevation. The boiling point has been elevated, it's been risen. So on the x-axis, you can see delta TF showing the change in the freezing point, and delta TB, the change in the boiling point. So right here in this one little phase diagram, you see 3 colligative properties. You see that as a result of dissolving a non-volatile solute, vapor pressures drop. So that's the first colligative property, the lowering of vapor pressure. As a result of that, freezing points also drop. There's a second colligative property, freezing point depression. And then boiling points go up. And there's the third colligative property, boiling point elevation. Okay, so vapor pressure is lowered. As a result of that, freezing point is lowered and boiling point is raised. There are 3 colligative properties. Does anybody need more time to sketch this?
Yeah, I'm almost done.
All right. While you're just finishing that, I'll blabber a bit here. So in the old days, when I taught this, we did not limit ourselves to non-volatile solutes. We also talked about volatile solutes. It gets quite interesting because if you have a solute that can evaporate, then there's 3 possible results if you put that solute in a liquid. If you dissolve a solute which is volatile, but it's less volatile than the solvent, then the overall vapor pressure will go down. If your solute is more volatile, for example, methanol is much more volatile than water. If you put methanol in water, the vapor pressure will go up because the evaporating methanol creates greater vapor pressure above the solution. But you can also have a solvent and a solute with roughly equal vapor pressures. Then when you mix those together, the solution's vapor pressure is about the same as the pure solvent. So if your solute were volatile, you can have different situations with the vapor pressures. Okay, we're not going to deal with that. We're only going to deal with non-volatile solutes where the solute does not evaporate. Okay. So the key idea there was that the vapor pressure dropped as a result of dissolving the non-volatile solute. But why does it drop? This explanation is pretty simple and therefore too simple, right? But it's a simple explanation that'll give you something in your brain to sort of rationalize what could be happening. On the left, you see a container with pure liquid, pure solvent. Those little green balls are the particles of the pure solvent. It's a volatile solvent, so some of it evaporates. There's a lid on the container, so it reaches equilibrium, and there's a vapor pressure. that vapor pressure is around 3 units, according to the meter there. On the picture on the right, you have the same solvent, but now you've added a non-volatile solute. The yellow particles are non-volatile solute. Those particles do not evaporate. That's what non-volatile means. Look at the surface of the liquid in the solution on the right. Where there used to be only solvent particles, now you have solvent particles and some solute particles. Those yellow particles don't evaporate. So you have fewer particles at the surface that are able to evaporate. Does that make sense? Some of the surface positions are now occupied by non-volatile solute. So therefore, with less solvent at the surface, there'll be less evaporation from the surface, and therefore there'll be a lower vapor pressure. That's the explanation. So now the little gauge says 2 units instead of 3. Okay. Is that relatively simple to understand, folks?
Yes.
Yeah.
Anybody confused by that? Okay. Can I move on? Here we go. There's an interesting and in some ways hard to believe extension of what we just talked about. Sketch what you see here. This years ago, this was an AP exam question. On the new exam, it's unlikely to show up there, but sketch it. It's very interesting and hard to believe. Take a beaker and put pure water in it. Take another beaker and put a solution like sugar water or salt water. So on the left, pure water. On the right, a solution with water and a non-volatile solute. Cover that with another container. Completely seal it up. So no air, nothing can get in or out. And then leave it for several days, maybe a couple of weeks. When you come back, you're going to find what you see over here. Hard to believe. The water beaker is now completely empty. It totally evaporated. But it didn't just evaporate and go into the air, because look at the aqueous solution. The level of liquid in the aqueous solution has gone way up. So it's as though somebody reached in and poured the water into the solution. But of course, nobody did that. The water simply kept evaporating. And as it evaporated, it also condensed into the solution. So it's as though water just left from one beaker and went into the other beaker until there's no more water on the left. Do you believe that this would happen? That seems crazy, doesn't it? Why is it happening? Well, we just said that if you dissolve a non-volatile solute, the vapor pressure above the solution should be lower than above the pure solvent. If you let me anthropomorphize here for a moment, it's as though the water beaker on the left wants a higher vapor pressure above it than the solution does. The solution is trying to achieve a lower vapor pressure, but the water is trying to achieve a higher vapor pressure because the solution should have a lower vapor pressure, according to what we just said. So imagine the solution wanting to have a lower vapor pressure. So some water vapor from above condenses into the solution. As that water vapor condenses, the vapor pressure goes down. There's less water vapor, so the vapor pressure goes down. So now the solution's happy. It's got a lower vapor pressure. But then the water says, damn, the vapor pressure just went down. I wanted a higher vapor pressure. So the water evaporates a bit. And now the vapor pressure goes back up and water's happy. But Now the solution's not happy. There's too high of a vapor pressure. So the water condenses again. And when will this end? When will that end? Well, the solution's volume is going up because water keeps condensing in it. So the concentration in that beaker is going down, but it never goes to zero. It's always going to be a solution. Even though the concentration goes down, it's always going to be a more concentrated than pure water, right? So as a result, the solution will always be trying to achieve a lower vapor pressure. The water will always be trying to achieve a higher vapor pressure. So this will not stop until there's no more water. So you end up with an empty water beaker and a much fuller solution beaker. Now, one thing to point out is the picture on the left is a bit overly simplified because it shows those arrows leaving water and going to the solution. It leaves you with the impression that water is only evaporating and the solution is only condensing. That's not true. There is evaporating and condensing in both beakers, but in the water beaker, there's more evaporation than there is condensing. In the aqueous solution, there's more condensing than there is evaporating. So therefore, ignore the smaller process in each beaker. Okay. I hope that makes sense. Does anybody have a question about that?
When water enters the solution on the right beaker, why does the pressure lower?
So what's causing the vapor pressure, Jean? What creates vapor pressure? The presence of the vapor molecules, isn't it?
Yeah.
So these water molecules in the air are creating vapor pressure, aren't they?
Yeah.
So when some of those molecules condense, there's fewer vapor molecules above the beakers, aren't there?
Oh, okay. Yeah.
And if you have fewer particles, Avogadro's law from our gases unit, if you have fewer moles of gas, you'll have less pressure, won't you?
Yeah.
Okay.
Okay. Thank you.
All right. So mathematically, we can describe the lowering of vapor pressure by something called Raoult's law, one of the cooler names in chemistry, Raoult's law. It's a pretty straightforward concept when you look at it and understand what it is you're looking at. So Raoult says that the vapor pressure above the solution, so PA, is equal to the mole fraction of the solvent in the solution, so XA, times the vapor pressure of the pure solvent. Pure is designated with the degree symbol here. So the little degree symbol means pure. So keep in mind that the solute is not volatile. So the solute does not contribute to the vapor pressure. Only the solvent contributes to the vapor pressure because only the solvent is volatile. So what Raoult's law is saying is that as a result of dissolving the solute in the solvent, you have a mole fraction of solvent less than 1, right? If you have pure solvent, the mole fraction is 1. It's 100% solvent. But if you start dissolving something in the solvent, then the mole fraction of solvent will go down. Maybe it's 0.9 or 0.8 or 0.7, and the mole fraction of solute goes up. So they have to add up to 1, right? The vapor pressure is caused by the solvent. So the subscripts here are all A's. The A refers to the solvent here. So the vapor pressure above the solution is the fraction of solvent in the solution multiplied by the solvent's pure vapor pressure. It actually makes sense. If the solution is half solvent, then the vapor pressure is half of what it used to be when it was pure. If you're using Raoult's law to solve a problem, don't use subscripts like these. Don't just put A's in there. Put meaningful subscripts. So if you were talking about water, maybe you'd put a W instead of an A. So the A here is just a generic subscript. In an actual problem, put a subscript which is meaningful. There are several permutations of Raoult's law problems. The simplest is what we'll look at on the next slide, is just using it to calculate the vapor pressure above a solution. That's the most straightforward way to use Raoult's law. The better way to use Raoult's law, the way that's actually how you use it in a lab setting, is you would measure in the lab the vapor pressure above a solution. If you measure this in the lab, and you know this, you know the vapor pressure of the pure liquid, you can look that up in a book or on the internet, then you can calculate the mole fraction of solvent in your mixture, in your solution. So in other words, carefully measuring vapor pressure above a solution lets you calculate or determine the concentration of your solution, right? We're going to know the mole fraction of the solvent and therefore also the mole fraction of the solute. And if you think of the kind of problems you were doing yesterday, if you know the mole fractions and say you can also measure density is pretty easy to measure, then it's possible by measuring vapor pressure and measuring density, maybe you can calculate the molarity or the molality or the mass percent from these simple measurements in the lab setting. You can also use it to determine things like molar mass, which is a much more powerful use. If you have a solute whose molar mass you don't know, you can use Raoult's law to determine that. We'll see an example of that later. So take a moment and write this question down. Where it says MW, that's an old term for, it's called molecular weight. We would say molar mass today. So what's the vapor pressure above a sugar solution, sucrose? The molar mass of sucrose, 342.3, prepared by dissolving 158 grams of sugar in 641.6 grams of water at 25 degrees Celsius. Think about that. 641 grams of water, that's like 641 milliliters of water. It's like 2/3 of a liter. 160 grams, 158 grams of sugar, that's a lot of sugar, right? 158 grams. If you dump that sugar in the water and stirred it up to dissolve it and tasted it, you'd say, wow, that's a pretty sweet, pretty concentrated solution, right? What's the vapor pressure above this solution? That's what we're going to calculate. Okay. We're given the vapor pressure of pure water. Of course, you can also look that up in your data booklet. Vapor pressure of pure water at 25 degrees is only around 23.76 millimeters mercury. Now, if this were a multiple choice question, it's possible you could pick the answer without doing any calculations. In a multiple choice question, you'd be given some choices. If one of the choices was bigger than 23.76 millimeters mercury, well, that would be impossible because you're dissolving a non-volatile, sugar doesn't evaporate, solute in water. The vapor pressure has to go down. So it couldn't be bigger than 23.76. It also can't be equal to 23.76 because it has to go down. So maybe there's two choices on your multiple choice question. You could just cross out because one went up and the other stayed the same. Now there might be two more choices left. So maybe you got a 50-50 chance, or as you'll see by the end of the question, maybe you could have canceled out one of those other choices as well. So why don't you start by writing down Raoult's law. Don't put subscripts of A, put W's. So, because we're talking about water here. So the pressure of water, PW, and of course that's above the solution, would be equal to the mole fraction of water, so XW, times the vapor pressure of pure water, so PW with the degree symbol. So is this question pretty straightforward? Yes, no?
Yes.
We know PW with a degree symbol. We know the vapor pressure of the pure water. And you gave me the masses of sugar and water. Can I go find the mole fraction of the water? Yeah, right? So I'm going to pause here and let you do that. So there's your moles of sugar, moles of water, and there's the mole fraction of water, 0.987. What does that mole fraction mean? It means that of all the moles in this solution, 98.7% of them are water, despite the pretty high mass percent of sugar, because sugar's mole or molar mass is so much bigger than water's molar mass, you still have many more moles of water present than sugar. And that means you have many more particles of water also, doesn't it? Right? And if you have more moles, you also have more molecules, right? Avogadro. So now that we have the mole fraction of water, calculating the vapor pressure is straightforward. The vapor pressure above the solution is just the mole fraction of water in the solution multiplied by the vapor pressure of the pure water. The actual answer, who cares? The more interesting thing to take away from this is that even in this pretty concentrated solution in terms of mass percent, the vapor pressure dropped only a little bit, right? So does the vapor pressure drop? Yes. Does it drop a lot? No. Okay. So you want to make a note of that. Vapor pressures drop, but not hugely. So coming back to that possible multiple choice question, maybe one answer was to vapor pressure went up. Another answer is it stayed the same. A third answer is the vapor pressure is now 1/10 of what it used to be. None of those answers would be reasonable. A fourth choice shows the vapor pressure dropped and just a little bit. Well, that's likely going to be the answer, even without calculating anything. All right. So we're going to skip over this. So we used to talk about volatile liquids. It was quite interesting. We got two equations, two unknowns, and Dalton's law. It was pretty cool, but we'll skip that. So we're going to talk now about boiling point elevation and freezing point depression, and then we'll stop there probably for the day. So boiling point elevation, we saw earlier from our phase diagram that because the vapor pressure dropped, the boiling point increased for a solution. There's a simple mathematical formula here to calculate the change in the boiling point. I emphasize that word change in boiling point because a lot of people will make the mistake of thinking they're calculating the new boiling point. No, you're calculating the change in the boiling point. So for example, if you were doing a problem where water was your solvent and you calculated the change in boiling point was 3 degrees Celsius, well then the new boiling point would be 103 degrees. Water boils at 100 degrees and boiling point goes up. So if you had a change in boiling point of 3 degrees, the new boiling point would be 103. In brackets there, the new boiling point minus the pure liquid's boiling point is equal to, now I'm going to talk about this a little bit more in a little bit, but I, which I'll give you a name for it in just a moment. I didn't put it on this slide for some reason. I is called the Van Hoff factor. I'll spell it for you on the next slide. Just wait a moment. The M here, if I were doing my own notes, I would put a triple bumped M, not a double bumped M like this, because you don't want to confuse it with mass. It's the molality of the solution. I mentioned when we studied molality that it's not a very common unit for concentration, but I said it's used in one particular area, and this is it. For doing these kind of calculations, molality is usually used. The K at the end, KB, is it's got a big ugly name. It's the molal, because we're using molality, boiling point elevation constant, okay? The molal boiling point elevation constant, or the boiling point constant, if you like an abbreviation. In your data booklet, you have a table like this, so you don't need to copy the table, but you might want to note for yourself, look in the data booklet on the last page, there's a table of solvents, their boiling points, their boiling point constants. It'll also show their freezing points, and as we'll see, their freezing point constants as well. So we know what the M is, the molality of the solution. KB is just a constant, the boiling point constant. And I'm going to talk about I in just a moment, the Van Hoff factor. But look at it just purely from a math perspective. When KB is larger, you're going to get a larger delta TB, aren't you? So when KBs are larger, you get larger changes in boiling point. So looking down at the bottom table, KBs are based on the solvent you're using. So when you know the solvent in your solution, you look up the KB value for that solvent. Of these four solvents, camphor has the highest KB, 5.6. So if you had a solution with water as a solvent, another one with benzene, another one with chloroform, and one with camphor, and they all had the same molalities, then the camphor would have the highest change in its boiling point because its KB is largest. Water would have the smallest change in its boiling point because water's KB is smallest. We're going to see in a moment, freezing point depression is the same basic formula. So there's a KF as well. When you look at camphor, you see its KF is huge. It's almost 40. So when you dissolve something in camphor, the freezing point of the solution is going to drop a lot. If you dissolve something in water, the freezing point will drop, but not by much. The KF is only 1.86. Looking back at the formula again, molality is a form of concentration. So the higher the molality, the higher the concentration, the greater will be the change in boiling point. I think that's kind of obvious. If your solution is so dilute that it's almost pure water, then not surprisingly, it's going to boil at close to 100 degrees and it's going to freeze at close to 0 degrees. But if your solution is very concentrated, then not surprisingly, it's going to boil, a reasonable amount higher than 100, and it'll freeze a reasonable amount below 0. And then there's that Van Hoff factor, which we're going to talk about, okay? So freezing point depression has the same basic formula as boiling point elevation. Delta TF is I times molality times KF. And there you can see the spelling for the Van Hoff factor. before you, we're going to derive an equation as it says there for molar mass. Before we do that, let's talk about the Van't Hoff factor. What exactly is it? I'm going to open up my morning notes and just cheat. All right, so the Van't Hoff factor, what is it? You could put that little title down. What is a Van't Hoff factor? You might want to remind yourself that colligative properties depend on the number of particles in the solution. So they depend on the number of particles. In the example I used earlier, I said sodium chloride and potassium nitrate. They'd have the same boiling points, the same freezing points, if you had the same concentrations of solutions. And I said that's because they both had, two particles in their formulas. So if you put 1 mole of NaCl in water, 1 liter, you'll have 2 moles per liter particles. Similarly, if you put 1 mole of potassium nitrate, you'd get 2 moles per liter of particles. Well, where I'm getting that 2 from, that's the Van't Hoff factor. So the Van't Hoff factor is just the number of particles produced, the number of moles of particles produced when 1 mole of solute dissolves. So the number of moles of particles produced when 1 mole of solute particles dissolve. For example, these salts, sodium chloride, potassium nitrate, lithium hydroxide, calcium sulfate, if you were to dissolve 1 mole of any of those 4 salts, you'd get 2 moles of particles. In the case of sodium chloride, you'd get 1 mole of sodium and 1 mole of chloride. So you'd get 2 moles of particles. In the case of calcium sulfate, you'd get 1 mole of calcium and 1 mole of sulfate. You'd get 2 moles of particles. So for those salts, the Van't Hoff factor would be 2. More specifically, the expected Van't Hoff factor, the theoretical, the ideal Van't Hoff factor would be a 2. Other salts, here's sodium sulfate, calcium chloride, and copper 2 nitrate. Each of those salts, if you dissolve 1 mole, will produce 3 moles of particles. For sodium sulfate, you'd get 2 moles of sodium and 1 mole of sulfate. You'd get 3 moles of particles if you dissolve 1 mole of sodium sulfate. So for those particles, for those solutes, I would be a 3. For these guys here, K3PO4, if 1 mole of that dissolves, you're going to get 3 moles of potassium and 1 mole of phosphate. I is going to be a 4. All of these examples are salts. They're ionic compounds. Well, when you put them in water, they break apart, which is why their Van't Hoff factors are 2, 3, and 4. When they dissolve in water, you now have ions floating in the water. Those ions can move around in the water. Just like electrons moving inside a metal, ions moving inside water represent the possibility of electric current. If the ions can move through the water in one direction, then you have electric current in the water. So these are referred to as electrolytes.
Please excuse the interruption.
Okay.
Apologies for the timing of this announcement.
Okay, that was cryptic. Let's see what important new information is coming from the division. So anything that produces ions when dissolved in water is called an electrolyte because the water then conducts electricity. You may have heard of the word electrolytes. When you work out or exercise, you sweat a lot. And when you sweat, you can be losing salts from your body. So you can drink water, but that quenches your thirst, but it doesn't replace the salts. If you drink some sports drinks, those sports drinks will have salts in them that replace what was lost in the sweat. And so they contain electrolytes. Some solutes are not made of ions. They're covalent. They're molecular compounds. For example, sucrose, C12H22O11, naphthalene, C10H8. So when you look at their formulas, go back to your nomenclature unit, those are not ionic compounds, are they? So those would be referred to as non-electrolytes. If they're non-electrolytes, when they dissolve in water, they don't break apart into ions. So if you dissolve 1 mole of sucrose, you're going to get 1 mole of particles in the water. If you dissolve 1 mole of naphthalene, not in water, it's not soluble in water, but you dissolve it in alcohol maybe, you'll get 1 mole of naphthalene particles. So for non-electrolytes, the Van Hoff factor will be a 1. Okay. All right. On the last slide, you were asked to take the freezing point depression equation. So delta TF equals I KF times molality. And we're going to use it to find a molar mass. Okay. This is these colligative properties we're studying them in part because they have applications in the lab. If I gave you in the lab a solute and I said, identify this, one way to identify a solute is to determine its molar mass, right? Maybe you're going to do an empirical formula and you want the molecular formula. You need the molar mass to do that. Well, you can find molar mass through Raoult's law. You can find molar mass through freezing point or boiling point changes. How? Do you see molar mass in that formula? Anybody? Anybody?
No.
You have to look closer. Is there a molar mass in that formula? Yes. Yes, there is. Can someone tell me what I'm going to do first to reveal the molar mass?
Write molality as moles of solute over kg of solvent.
Very good. So the change in freezing point can be rewritten as the Van Hoff factor times Kf. Molality is, as Hisham just said, moles of your solute divided by kilograms of your solvent. Now, Camille, thank you for saying, no, you don't see molar mass. I appreciate that. Do you now see molar mass?
Yes.
Where is the molar mass?
Isn't it with the moles of solute?
It is, right? How am I going to rewrite moles of solute? Just like we did in the ideal gas law many times. Moles is equal to what?
It's equal to the change in.
No. Just a bit way back in our stoichiometry unit. What was moles equal to?
Oh,
It's a little
mass
formula
over
for
molar
mole.
mass.
Mass over molar mass, right? So we can change moles of solute to say mass of solute over molar mass of solute, can't we?
Yeah.
Boom. There we go. Now that it's kind of like taking molality and blowing it up twice, right? Blow it up once and you get moles of solute over kilograms of solvent. Blow it up another time and you get mass over molar mass. Now do a little tiny bit of algebra and make that say molar mass of solute equals. Since the molar mass is in the denominator, just multiply both sides by molar mass, and then move the delta TF by dividing both sides by delta TF. What you'll get is that the molar mass of the solute is I times Kf times mass of solute divided by delta TF and the kilograms of solvent. So just as a, we're almost done here, but just as a simple, I want you to do a thought experiment. Suppose I've given you an organic, not a salt, an organic solute. So you have some white powdery solute here. And I ask you, what's its molar mass? So you first test it to see what's it soluble in. What is it soluble in? So you test a few liquids and you find out that it's soluble in methanol. So then what do? Well, you take pure methanol. Here's a test tube with pure methanol. And what would you do first? Well, you do what you did in grade 9 advanced science. You determine the freezing point of pure methanol. Or more likely, you'd look it up in a book. Or if you're in the lab, you'd make a freezing point curve or something simple way to determine a freezing point. You find out that methanol's freezing point, let me look it up here. Hey Siri, what is methanol's freezing point? Talk to me, Siri.
Second. The freezing point of methanol is minus 98
Whoa.
degrees Celsius.
Okay, I'm going to change this, okay, because that's an unrealistic thing. Instead of freezing point, let's talk about boiling point. It's the same idea, right? Boiling point, we'd have a delta TB instead of TF. We'd have a KB instead of a KF. The same thing. So methanol, grade 9 science, you may remember, boils at 65 degrees Celsius. That's its boiling point. So now what do? You measure some of your solute. You measure its mass, right? Looking at our formula. So you weigh out 1 gram of your solute. You can weigh out whatever you like, but I'll weigh out 1 gram. You put a certain amount of methanol in a container, but you need to know the mass of the methanol because you need kilograms of solvent. So you used, I don't know, maybe you used 10 grams of alcohol. So that's 0.010 kilograms of methanol. Look at my formula. I know the kilograms of the methanol. I know the mass of my solute. I said it was a organic solute, which means what would its I value be? Somebody? What's the Van Hoff factor if it's not a salt?
1.
It's a 1. So we know I, we know mass, we know this mass. KB, well, we could just look that up, couldn't we? The back of our data booklet or on the internet, we can look up the the boiling point constant for methanol. Then the last thing I need is the change in boiling point. So I know the boiling point of pure methanol. So what do? I just add my solute to the methanol and dissolve it. And I measure the boiling point of this solution. And suppose it boils at 66.2 degrees Celsius. Just suppose. That's the new boiling point. It went up. Then what's my delta TB going to equal? What's delta TB?
1.2.
1.2 degrees Celsius, right? So look back at our formula. We know delta TB is 1.2. We know the mass of the methanol. We know the mass of our solute. We know KB. We looked it up. And the solute was a non-electrolyte, so I is a 1. Boom. We've got the molar mass of our solute there, don't we? All right. So that's the power of this colligative property. Not that you want to calculate a boiling point of solution. Like, that's interesting that you could calculate boiling points. But the more interesting, more powerful thing is the use of this to determine something like a molar mass that I can identify as solute, right? So that's in a chem lab situation, that's a pretty powerful thing to be able to find a molar mass of a solute. All right, so we're going to stop there. Tomorrow, we're going to talk about the last of the properties, the osmotic pressure. and then we'll practice some problems on these things. I've given you a bit of a clue here as the kind of questions we'll do. We'll practice them tomorrow. All right.